Right, so welcome to lab number 2. I hope you had the chance to look at the problems for the lab. Okay, so please start working on it. We have made sure this time that Jupyter Notebook is installed in the virtual machines. Is there anyone who's facing issues with getting the virtual machine working? Okay, good. And those who have started the virtual machine, can you open Jupyter Notebook? Right. So please have a look at exercise number 1. Spend a couple of minutes and try to write the program. In the meantime, what I will do is I will also try to write the program myself, and you can have a look at the board. And what we'll do first is we'll write the structure of the program. So we'll write some comments, and each comment will then expand into some sub part of the code. So this is quite helpful when writing programs. Rather than starting to write the program from line number 1, we try to break it into some structure and then try to fill in the structure. Any questions? Questions? Okay. So I've started to create the structure of the program. So if you are facing issues writing it yourself, please have a look at the board. So the program has 7 key parts to it. The first one is where we import the necessary modules which will be needed to call the functions needed in this program. The next is to define parameters. So you'll have some physical and numerical parameters for this problem that we'll have to define to start with. Then we'll define the full A matrix. Okay, so this case, if you read the exercise, it says that for the present case, you should be using you should define the matrix A and take the inverse of it rather than using the tri-diagonal matrix algorithm. For the first case, you invert the A matrix. Although that is inefficient, but that is suggested. I mean, just try it for the first time. And then we will be able to appreciate the difference, that the cost of computation between this method of calculating the inverse versus the method of using the tri-diagonal matrix algorithm for this case. Okay, so in this case we will be using inverse. So the third part of the structure is to define the full A matrix. Next we define the RHS vector, and once we have done it, we can calculate or evaluate the theta vector, the unknown temperatures, the vector of unknown temperatures, as the inverse of A dotted with R. So once you have done it, since we'll want to compare our numerical results and see with the analytical results and see how accurate our numerical evaluation is, so we'll also evaluate the analytical theta that's given as an expression here in part number 4 in the problem for theta analytical. So once you have done that, finally we will plot theta numerical and theta analytical on the same graph to see a comparison of the results. So theta analytical is the exact result. So we expect the numerical result to follow the theta analytical. So the closer our numerical result is to analytical, the better our solution is. Okay, so this is the overall structure of the problem. Now what I'll do is I'll start to fill it in, and then you can sort of copy it or just compare your results or your code with what I am doing. There are different ways to do it. You may be doing it slightly differently, but as long as you're doing the same thing, it should be all right. I mean, the same idea is being implemented, it should be all right. Good morning. Right, so let me quickly discuss what I've done till now. So we have imported 3 modules here: NumPy, Matplotlib, and Math. So NumPy is for the numerical modules. Matplotlib is for plotting, and math will be required for some functions needed in the uh, analytical calculation. You can actually use NumPy for doing this, but we have imported math explicitly. Now we have defined some parameters. So in this case, since we are dealing with a non-dimensional form of the equation, you see that there is only one pi parameter, and that is specified in the problem. So the only pi parameter here is this HPL square by KA. So basically, rather than changing these parameters such as heat transfer coefficient or the perimeter of the fin or the area of the fin or the thermal conductivity or the length of the fin independently, what happens is that ultimately our solution, non-dimensional solution, is only a function of this parameter. So if you double the h and double the k, the solution remains the same in the non-dimensional space. You can always go from non-dimensional to dimension space by using the whatever transformations we have used. So if you calculate the solution to this problem for theta non-dimensional versus x non-dimensional, you can go from this space to theta versus x space by using this transformation. So it's always recommended to work in non-dimensional space because that reduces the number of parameters, as you already have studied in various courses such as fluid mechanics. Okay. That's the benefit of working with non-dimensional forms. So since there is only one pi parameter, and it's suggested in the problem that you can use pi equal to 0.01. So we use that. So we specify or we define pi equal to 0.01, and n is the number of n plus 1 is the total number of nodal points, which includes 2 boundary points. So we use n equal to 10. That's again specified in the problem. So in the later problems, we'll play around with these parameters and see how they affect the solution. For now, we will just program the solution for one set of numerical parameters. The next is to define the values of h, a, b, and d. So h is your delta x, the mesh size, which is 1 upon n. Since you have a total of n plus 1 point, so that means that you have a total of n intervals. Okay, so 1 upon n becomes the delta x, or h in this case. And if you look at your notes, you may already have done that. So the diagonal, above diagonal and below diagonal vectors, in this case, they all had, they were all constants, because if your delta x is fixed, then the above diagonal, below diagonal, and diagonal terms are all, all the diagonal terms are the same. Similarly, all the above diagonal terms are the same, so on. So rather than, what we do is we evaluate the value of a, b, and d, and then we'll use that to define the A matrix. Now in Python, to define an array, the easiest thing is you define it using the zeros or the ones function. So in NumPy, there's a zeros function. What it does is it takes in as an input, it's a function, so it takes in as an input as the size of the array that you need. So array is a two-dimensional array, so n plus 1 by n plus 1 is the size. So what we are doing is we are creating a linear system for the complete theta vector, including the boundary points. So if you include the boundary points, the total number of points you have in the, or the total, the size of the A matrix will be n plus 1 by n plus 1. Again, this was discussed in the lecture, so there is nothing new here. You have I found the linear system in the lecture. So once you have declared an A array which is all zeros, now we have to fill it, because see, the reason I started with all set of zeros is because mostly it is zero. It's only 3 diagonals which are non-zero, everything else is zero. So what I'll do is I'll start with all zeros and overwrite the non-zero terms. So first, since the first equation is trivial, it's just 1 times theta naught is equal to some theta initial, so some theta boundary on the left. So we simply use A00 equal to 1. That's the first row of A matrix. After that, before we start defining all the intermediate rows, we define the nth, the boundary condition on the right hand side. So there we have to define ANN and ANN minus 1, which again you can have a look at the notes for this. And by the way, the notes are available on Moodle if you want to look at them right now. And then for the intermediate points, we run the loop from I equal to 1 to n minus 1. So this range function starts from the first index. So this is 1. If you don't specify it, it starts from 0. So it starts from 1 and goes all the way to n minus 1. So whatever is the last number you pass into range, it will go till the last number minus 1. So this goes from 1 to n minus 1. And that is what we want, because for 0th and the n plus 1th point, we already have specified that. Or for the 0th and the nth point, we already have specified. There's no n plus 1th. Okay. Because in Python, everything starts from 0. So to have an total of n plus 1 points, you can start from 0 and go all the way to n. Okay, so ai is d, all the diagonal terms. ai minus 1 is the below diagonal term. That's the ith row, but I minus 1th column. That's one left of the diagonal term. And ai plus 1, that's the above diagonal term. Okay. So this allows us to define the A matrix. Then next we define the RHS matrix. Now after non-dimensionalization, one good thing that happens is that the right hand side matrix for the governing differential equation becomes 1 identically, rather than it being h times something that we had in the notes that we saw. Non-dimensionalization results in the right hand side vector all being 1. So you can also have a look at the handout that was shared on Moodle on non-dimensionalization. I suggested you to have a look at it after the lecture. So if you look at it, you will see that the non-dimensional form is derived there. So you'll see the right hand side is identically 1. So this makes things much easier for us. And it makes it all zeros. I'm sorry. It's actually good to have a look at it. I might have made a mistake here. So this was the handout that was shared. So we start with the governing differential equation, and then we substitute theta and x in terms of non-dimensional parameters, the way we have defined theta non-dimensional and x non-dimensional. So we are going from physical space to non-dimensional space here. And once you do the substitution, what you will get is this equation. Right. So if I discretize this, what I will get is the right hand side will become 0. Earlier, the right hand side was not 0. You had a beta times theta f on the right hand side. But this time, because you have taken theta minus theta f upon theta naught minus theta f, so theta minus theta f combines into one theta non-dimensional. So that makes things a bit simpler numerically as well. So right hand side is 0 in this case. Similarly, first boundary condition becomes theta not equal to 1, rather than theta not being equal to some value. It becomes identically 1, and the right hand side is the same. It's theta n minus 1 is equal to 0. So this was a linear system that was discussed. Now this is, I think we discussed it excluding the top boundary, but this time we are including the top boundary, so we will get that 1 times theta naught as well. Okay.
Sorry, n is the intermediate number. N is the intermediate points. Number of intermediate points.
Capital N.
Yes, sir.
Capital N is the total number of discrete points in your domain.
Oh, on the boundary also.
Total number. So if n is 10, for example, in this case, what that means is you have a total number of 11 points on the domain, which includes 2 boundary points. So that will be a total of 8. We have a total of 0 to n, right? So you have a total of 11 points. So that means you have 9 intermediate points and 2 boundary points. So for intermediate index or running index, we use I for space. So you can see that I goes from 1 to capital N, and for each I you evaluate the value of the terms in the A matrix. Okay, so right hand side we start with a vector of size n plus 1 as expected, all zeros, and then we overwrite the 0th index as 1, as we saw in the non-dimensional form. So this, and very quickly, I mean, there's not many lines of code. In fact, we've only written around 27 lines, and we have been able to initialize A and R. So the next step will be to calculate or evaluate theta by using A inverse times R, or in this case, we have to use the dot function as we saw. Dot does the expected thing for us. Any questions till now? Any other questions? Okay. So I have evaluated theta as the dot product. So dot is a function, and then inverse of a comma r is what is passed to dot. And now what I'll do is, before plotting it, I'll just print it and see if this is working, if my code is working. It's actually in the function np.zeros, we pass a tuple. So the first bracket is for passing the function, the second bracket is for the tuple. It takes a tuple of size n plus 1 comma n plus 1. So that's the reason you see double brackets. Right. So now it runs, and I can see some values of temperature which I think are looking all right. So these are the temperatures starting from the left boundary all the way to the right boundary. So this is a fin, remember. So left boundary is hot, and as you go right, it will get cooler. Right, so let's plot it now. So for plotting, we'll have to define an x. So we'll be plotting, x is actually, so theta and x here are non-dimensional space. So we'll define some discrete x so that we can plot theta with that x. Right. So we have plotted theta numerical against theta analytical. It's worth I mentioned the labels. Right. So we can see the analytical is the orange one, and the blue one seems to follow the analytical one with the same trend, except that there is some difference between the values, which is expected because see you have n equal to 10. So delta x is pretty large. It's of the order of 0.1 here. So x is going from 0 to 1. Delta x number of points is 10. So you have a 0.1 as delta x, which is quite large because your method here, we are using, what did we use? We used center difference. So the method is second order. So error is 0.01 of the order of delta x squared. So what I can quickly do is, now I can change the value of n. So let's make it 1000 and then run it again. Shift enter will run it again. And now we see that the blue and the orange seem to overlap. Okay, so I can actually just to see the difference, I can use stars here, and now you see that the stars when plotted, you can see that they're exactly overlapping each other. Okay, is the idea clear? So I'll share the code with you, and don't worry, you can try it yourself. So the next exercise is to solve problem number 1, but this time with tri-diagonal matrix algorithm. So I already have solved it. So what I'll do is I will copy it and paste it. I mean, you'll get the code because we don't have enough time here. There are many exercises here. So a couple of them I'll expect you to do it yourself. So this is the code for exercise 2 where we are using TDMA. So you can see that we are not evaluating a matrix this time. We are using that forward elimination and backward substitution algorithm. And if I run it, I get, I mean, the error is not biased towards one end. You can see that the numerical one underestimates in the first half and overestimates in the second half. I think n is also equal to 10 here. So if I make n a bit larger, 100 let's say, and run it, so we can see it follows it quite nicely. Okay. Now the reason we are using TDMA is because it's faster. Well, in Python it's very easy to check that. So what you can do is on the top of the code, there's a magic command for IPython or Jupyter notebooks, which is time it. So you use $% for magic commands, and you write time it, and I will run it this time. What I'll do is I will suppress plotting, because what this time it does is it runs this code many times, sometimes thousands of times, and averages the runtime. So it's a statistical way to calculate because if you run it only once, there is a lot of sometimes the significant time is spent in sending it to the registers and then bringing the results back. So rather than wasting time there, we want to see how much of a processing time is needed. So it sends the data to the registers and then it runs it many times and then brings it back. So that way is it is able to check the runtime rather than time needed for other things as well. So let's suppress the plot. So control / will comment out all these commands, and then we will run it. So it will take some time because it's running the code multiple times. And as a result, what we see is, let's look at only the average. It took approximately 88 microseconds per run from a total of 10,000 loops times 7,000 70,000 is how many times it ran. But on an average, it took 88 microseconds. Pretty quick. Now let's just do the same thing for the same value of n. So n is equal to 100 for this case as well. It's actually printing the values of pi as well. It'll take a lot of time to print it 10,000 or 70,000 times, which is not what I expected. So we will have to stop it. So I'm running it again after restarting the kernel. So it took 260 microseconds. So you can see that 88 microseconds versus 260 microseconds. And this was n equal to 100 as well, right? So that is what we had earlier. Yeah. So definitely there's a difference, right? 3 times slower. And actually, if you increase the value of n, which typically you would want higher values of n so that you have better accuracies. You will see that TDMA actually starts dominating. So it took 59.6 milliseconds. So 1 millisecond is 1000 microseconds. And if I make it 1000 here, so it's less than 1 millisecond. So 1000 microsecond is 1 millisecond. So it's actually 60 times faster now. 60 milliseconds versus less than 1 millisecond. Okay. You can see that TDMA definitely is faster. And what it does is, depending on how fast the code is running, it will run that number of loops. That's the reason we are looking only at the average. Because if the code is running really slowly, it won't run it for very long iteration. Otherwise, you have to wait for a very long time. So it decides how many iterations to run for the averaging, so that you get a result in realistic amount of time quickly enough. Is that clear? So in computing, we do that. I mean, it's always good to do some sort of benchmarking as to how fast, not benchmarking, profiling. So it's called code profiling. So you profile the code and figure out how fast it is running. In profiling, we also see subparts of the code. So which subpart is taking most amount of time. So you would time separate parts. So there are more advanced ways to use the time function and time different subparts of the code, so that you can figure out yourself. Our aim is not to learn detailed computing ideas, but just to be able to program the CFD algorithm that we are learning in the class and see how they work. So this is exercise 2. The rest exercises 3 and 4, I'll give them as homework to you. So exercise 3 is actually quite interesting. It plots theta versus x, the same way we have done in the previous 2 cases, but this time it does it for different values of n. So what you will do is, you will have one theta analytical, but you'll have many numerical thetas each for different value of n. So what you'll see is as your n value increases, your numerical theta approaches the theta analytical. It's not that difficult to do, except that in programming we have to run the whole program for different values of n. So all that running goes inside a loop where n goes from 10 to 10,000 in these steps. So it's asked what happens as you increase the value of n and y. So is it desirable to choose a very large value of n? Because as if you have a larger n, you get more accurate result. It's quite obvious. But does that mean we will choose an extremely large n? There is a trade-off here between accuracy and computing time. So we have to choose a sweet spot as to where we have to, which n we have to, what is the optimum value of n that we have to choose. And this process is called grid independence test. So grid independence means beyond a certain value of n, your solution will not show much improvement. Okay, so for that, what we do is we plot the value of n on the x-axis and theta at some location. You cannot plot all the theta, so you choose theta at some location and you plot that at on the y-axis. So you have n on the x-axis and theta at some location on the y-axis, and you will see that that theta will actually show some sort of flattening curve. So whenever it gets flattened enough, you say that we will not go beyond that n. Otherwise, you're simply adding more computation time without giving you much benefit in terms of accuracy of the solution. So that's called grid independence test. So you're expected to plot the theta with n here. And the last one is to get the order of convergence. So this is a second order scheme. Again, I expect you to do it, but I would want to run it for you and show you what you are expected to plot, because sometimes there's a confusion here. So here what you'll do is you will plot the value of delta x on the x-axis, and the y-axis you will have error. So what you do is you calculate the theta analytical and theta numerical at x equal to 0.5, center of the domain. You could choose any other x as well, that is your choice. And then you plot it on a log-log graph. Because remember, we expect our error to be of the order of delta x squared. So if you take the log of both sides, your slope of the line will be the order of convergence. So if I run it, so here let's look at the slope quickly. So delta y is minus 6 minus 10, so that is 4. So 4 units on the y-axis for this whole straight line, and 2 units on the x-axis. So 4 by 2 is 2. So the slope of this line is 2. And that is what we expect. The slope of the line, this is error versus delta x on a log-log graph. So this is actually log error versus log delta x. Okay, so we see the line is, slope of the line is 2, and that is what we expected. So I expect you to do it yourself. I mean, see, the base code is still the same. We are still doing forward elimination, backward substitution, except that we are now running it for different values of n. So we create a list of n values, and then for each value of n, we'll run this whole code. So this whole complete code where you calculate the error as a difference between numerical and analytical values, it goes inside that loop, and you do it many times. And every time you run it, you store it, the value of error, into some outer array, and then you plot it. So please try it, and then after a couple of days, I'll upload the solutions to all problems. For the first 2 cases, I'll upload the solution right away on the codes folder in Google Drive. Okay. Any questions?